great technology!
Propellers are a zombie technology. Now, they still work great, but you will never see a major advancement in propeller efficiency. The propeller has reached its limits, which makes it very hard for manufacturers to convince you that they have the best propeller. They try to confuse you with a dizzying set of fancy graphics and made-up terminology. Now, to fight all of that confusion, you need to understand the basic physics of how propellers work and, more importantly, their resulting limitations. Did you know that all propellers have a maximum theoretical limit on their efficiency? This is called the Betz limit. Originally developed for wind turbine performance, it applies to any type of normal axial flow propeller, like the kind you put on the back of your ship. The Betz limit predicted a maximum efficiency of 59.3%. Let's round that off and call it 60%. Reality doesn't always match the simplified assumptions that went into the Betz limit, so we can see efficiencies that are slightly higher. A typical propeller hovers around 65% efficiency, and some very good propellers can even achieve a maximum efficiency of about 72%. But all these numbers are still close to the Betz limit, which shows us that it is fairly accurate and believable. But even worse, all of these practical implementations of propellers are already pushing past the Betz limit, which means we really can't expect them to push much further. They're already stretching the limits of those assumptions. Little known secret? The limit on propeller efficiency has nothing to do with the design of the actual propeller. Propeller efficiency gets limited entirely by the physics of how water enters the propeller. This is what I'm calling the propeller slipstream. Now, the full explanation of the propeller slipstream is fairly complicated, and at this point, fluid mechanics people usually need to resort to math. If you happen to be a math person, this is a wonderful, very satisfying explanation involving many Greek symbols and lots of pluses and minuses. But for the rest of us, we should stick to a more physical analogy, which is not perfect, but it conveys the main idea. For the moment, I want you to forget all of the details of how a propeller produces thrust. Let's just settle that we know it produces thrust. We know that a propeller must produce thrust, pushing the ship forward. But now, Newton's third law reminds us is that if we want a thrust force forward, there must be an equal and opposite reaction on the water pushing back. Imagine this. You've got a ship fixed in the water. Now, to get a thrust, the water must shoot out the back of the propeller faster than when it entered the propeller. That acceleration of water is what creates the thrust. But now here's the catch. We pay a penalty for all the surrounding water. See, all the surrounding water sees that central core that's getting sucked into the propeller, and it thinks that looks very exciting, so it wants to come along for the ride. Catch is, it's not going as fast as that central core of the slipstream. So we have to accelerate that extra mass of water back up to our core speed just to keep up with the propeller. And only when it finally reaches the propeller can we actually generate thrust from all of that extra water. So in the end, our chunk of water is not a straight tube. It actually starts out as the same diameter as the propeller, but it expands as we move upstream. And this is what we call the propeller slipstream. Well, the Betz limit sucks. But although we cannot completely blow away the Betz limit, we do make a few modifications to get some modest gain. Now, up to this point, all of the theoretical discussions here have assumed that the propeller was somehow magically suspended in the middle of the ocean, with open water all around. But we know that's not reality. Real propellers are mounted close behind the hull of a ship. And that close proximity creates some very interesting interactions between the ship and the propeller. Some of those interactions help efficiency of the propeller, and some hurt it. Now, the three main interactions that we are going to look at today are wake fraction, thrust deduction, and relative rotative efficiency. Number 1, wake fraction. If a ship moves forward at 16 knot speed, the propeller does not see water traveling at 16 knots. There's a head twister. See, this is due to the wake fraction. Now, the water slows down as it fills in the gap behind the stern of the ship. So if the ship is traveling at 16 knots, the propeller might only see water moving at 15 knots. And that's due to that slowing down effect, the wake fraction. We measure this wake fraction as a ratio of the reduction in water speed at the propeller compared to the ship speed. Wake fraction typically varies from around 0.03 to 0.2. So we're saying it can adjust propeller efficiency by 3 to 20%. So wake fraction is a good thing, okay? Propellers generally are more efficient when the oncoming water stream slows down. And remember that it only depends on the hull, not the propeller shape. That's important because it lets us find out the interactions between the propeller and the hull, and then play what-if scenarios, trading out other propellers to see if we can improve things at all. Number 2, thrust deduction is the enemy of propeller interactions. Remember that a propeller generates a suction upstream of it. Now, this suction is part of what creates the thrust, but more importantly is how it interacts with the hull. This suction creates a field of low pressure in the water ahead of the propeller. That low pressure sucks against the hull of the ship. The problem is that low pressure and that suction actually pulls the ship backward and slows it down a little bit. The issue of this low pressure region gets attributed to the propeller. This is more of an organizational convenience. You see, naval architects, we typically like to keep the hull and the propeller separated as different concepts. So we're going to take this suction force and we're going to count it against the propeller instead of the ship's hull. So how we count that is a deduction in the thrust of the propeller. Thrust deduction gets measured as another ratio. We like ratios. This time we count it as the ratio of that extra drag force compared to the propeller thrust. Now, it would be nice if this were a small number, but the thrust deduction is typically somewhere between 0.05 to 0.2. That's a 5 to 20% penalty on your propeller efficiency. Number 3, relative rotative efficiency. Say that 3 times fast. The relative rotative efficiency finishes out our set of efficiency modifiers, and this is something of a catch-all for all the secondary interactions. See, the wake behind the ship is not a uniform speed, and that variation means that the propeller blades see different water speeds as they rotate around. When the blade is vertical straight up and down behind the stern, it sees slow water directly behind that stern. But compare that to the relatively clear water of the blade as it's horizontal and exposed to that running free stream. All of those variations in flow rate as the blade rotates around, all of those affect the torque required to spin the propeller. We call this variation the relative rotative efficiency, and that's the ratio of the propeller torque when you're measuring it behind the hull compared to the torque when you tested it in open water. Relative rotative efficiency can either be good or bad, and this ratio varies from around 0.95 to 1.1. So 95% to 110% on the propeller efficiency modifiers. So values below 1 are bad. They're showing that your propeller performs worse behind the hull. Although that is fairly common to customize the propeller and actually adapt it to the specific flow patterns of your vessel. In these cases, the relative rotative efficiency may actually go above 1. That's a good thing. It means your propeller does better behind the hull. So time to wrap it up. You add all of these interaction effects together with the thrust deduction and the wake fraction and our relative rotative efficiency, and the combination of all 3 of these can add up to a difference of around 10 to 15% modifier on your propeller's efficiency. Now, naturally, we want that modification to move in the positive direction, increasing propeller efficiency. And a good propeller designer can do just that. I wish all you want. Your propellers will never get significantly better than they currently are. They remain forever limited to the fundamental physics of fluid dynamics. No manufacturer can provide a miracle device to double your propeller efficiency. A typical propeller is always going to be around 65% if used correctly. The best propellers out there will only push that to maybe 72% at the top. So when considering your next propeller, remember these limits and arrive armed with reasonable expectations. Thanks very much. I'm Nick, the Naval Architect. Yes, we have reached the part of the show where I ask for tips. So please hand me your tips. In this case, I just need you to click that little subscribe button. Subscribe.